Hello, everyone. Thank you for joining for this news episode of Armstrong live stream. Today we'll speak about thermal decarbonization in light industry. My name is Rossen Ivanov. I've been with Armstrong for 25 years. Currently, I'm the managing director for Armstrong for Europe, Middle East, and Africa. And about 15 years ago, while I was involved on the service side of our activities, I had the pleasure to meet our guest of today, Mr. Alain Leiser. So Alain, can you briefly introduce yourself?
Yeah, hello everyone. Thank you, Rossen, for the invitation. So I'm Alain Leiser. I'm energy engineer by education. I've been working in the industry sector for 25 years, mainly I started with the chemical industry, and then I moved to the FMCG's business. Working with different companies, and I finished my career with Nestle, where I headed the Department of Environment for the water business. And I'm now an advisor, an independent advisor, working on this topic with Armstrong.
Thank you, Alain. So before we go into the technicalities of the conversation, how to decarbonize light industries and thermal in light industry, let's just set the stage and frame the challenge. What is the percentage of industrial heat? What is the contribution of industrial heat emissions in global greenhouse gases emissions? And how much of that heat is high temperature heat, or how much of these emissions are actually coming from low temperature heat?
Actually, that's massive. I mean, industrial heat is a real massive part of the energy that is consumed. Can say almost a third of the total final energy that is consumed in the world goes to thermal heat. Now, if we look at that from a carbon perspective, it would be in between 10 and 15% of this energy that is emitting the carbon. Now, you mentioned the fact that we have to differentiate the high temperature from the low temperature. Indeed, that's very important. But out of this total energy that we are talking about here, almost 30% goes for temperature below 150 degrees. So it's a big chunk of that we can address at the level below 150 degrees.
Yeah, that's quite interesting, because there are not a lot of studies about industrial heat and how to decarbonize that, but most of these are actually focused on heavy industry. Things like steel, cement, glass manufacturing, which are heavy contributor to these greenhouse emissions coming from industrial heat. But they also require a high temperature, and they have their challenge on their own. The decarbonization there probably will be done through electrification, direct electrification, or even carbon capture. What are the other type of industry which would require rather this low grade heat or low temperature heat? Can you describe us the kind of products they make?
Yeah, actually, the quantity of the energy at low grade is really going. It's big part with the FMCG's companies. So the food business, the consumer goods that you will find on the shelf of your supermarkets. So all those kind of product that need, I would say, basic process like evaporation and drying, those kind of conditioning. That's the kind of industry where you will find these low grade temperature need, and that's actually the major part of their heat. They do not need for those companies. They do not need to go to 1,000 degrees. They are getting there. That's historically, because they are generating the steam, and this is done in a combustion system. So usually they go they generate high temperature at the beginning, but what they really need at the end for that process is really a low temperature below 150.
Okay, so yeah, that's really eye-opening. These are all the products which we find in our kitchens, in our bathrooms, in our laundry rooms, which are all around us and we consume every day. Now, what amazes me is that these factories are actually quite different, even if they make exactly the same product for exactly the same company. They have been designed originally in a different way. The plant layouts are different. So that creates a challenge on its own, is how to implement a replicable technical solution when all these factories pretty much are having different current state, different starting point. At Armstrong, what we believe is that it's not about replicating exactly the same system from one side to the other. It's really about using the same methodology for discovering the current state, collecting all the data, which is one of the hardest parts at the beginning, is to get reliable and complete data. And then to imagine a roadmap of how to bring these current states toward a decarbonized end game. So we call that methodology optimize, minimize, decarbonize. These are the three parts in the methodology. We are going to speak about optimize in deeper detail in a minute, but let's cover first the minimize and decarbonize parts, which are probably the one that are the most discussed within teams working on thermal decarbonization. So I'll start with minimize. Minimize is about minimizing the demand for heat. It is really questioning, will this plant consume as much heat as it does today, 10 or 20 years down the road? There are new technologies coming in. A lot of the process equipment manufacturers are working, doing a lot of R&D to minimize the energy consumption and the heat consumption of their processes. We keep hearing things like called CIP, so clean in place, which means making the cleaning water without even heating it. While this is one of the significant consumers of heat today in these industrial sites. In other cases, about switching. You mentioned steam systems, so it's about switching from using steam, which is at high temperature, using maybe different energy, most of the time electricity, to do the same work. And this is typically the case when it's not about heating. So sometimes steam is used for creating vacuum, and there are electrical vacuum pumps. Sometimes steam is used as humidification, for humidifying the air, not for heating the air, but really just to add humidity to it. And in that case, more and more, we recommend using adiabatic humidification, which allows simply to inject water in the air. And it has another positive effect, is that it comes with certain cooling, which might be needed in the warm part of the year. So it's important to understand how heat consumption can be minimized down the road. However, from implementation standpoint, this typically doesn't come at the beginning, because it would involve typically a significant capex to replace the process equipment. So these capexes might be invested as part of the end of life cycle investment, but they should appear on the roadmap. It should be known that at one point the demand for heat is going to be decreased, so that we avoid overshooting with the other solutions we are going to bring. So that was the minimize part. Alain, can you tell us a bit about decarbonize? And decarbonize is really about decarbonizing the primary energy, which today is fossil fuel, typically natural gas or coal, which is being used for producing steam or hot water. What are the alternatives to these fossil fuels? And what are the pros and cons of each one of them?
Yes, Rossen. As you said, the objective here is really to replace the source of the energy, the primary energy. So the most obvious solution on the one that is used today is really a switch to electricity, and this switch to electricity has also some limitation. As you can imagine, in the light industry, the thermal heat represents almost 80% of the full energy that is consumed in this industry. So if we now replace all this heat with electricity and one-to-one replacement, I mean, this will multiply by 3 to 4 the need of electricity for such industry. So this is very, very difficult to supply today. And it comes also with a cost, because the cost of electricity, equivalent kilowatt hour, if you want, electricity compared to natural gas, for example, is in a ratio in between 3 and 5. So again, with the increase of demand comes also the burden of the bill at the end of the year that you have to pay for this electricity. So then you have the alternative of other renewable that you can use, like biomass, for example, or agricultural byproduct that you may have in the industry, which is usually a good solution, because when you are working in the food business, usually the food is coming from agriculture, so there is some byproduct that can be used to generate the heat in your system. So that's usually a good solution, but it's also very dependent on the situation, on the location. Is it available on that side? On that side, sorry. And the other aspect is that usually those bioenergy, if we are talking about solid bioenergy, usually they are not commodities. They are not tradable globally. They will be available on site, and that's where you will get them. And the fact that you can afford them will also depend on the distance you are from the source. And then there is all the other renewable, like the solar thermal, geothermal, for example, which also will depend on the location. And for the solar, obviously, there is the difficulty of the fact that it is intermittent. It's an intermittent source of energy, which means that you need to store that energy. Now, talking about storage, the storage of tomorrow is very likely to be the hydrogen. The hydrogen will come in the next 10 years, definitely. There is a huge investment those days for hydrogen. So producing the hydrogen with available renewable electricity, windmill, and so on, and then using this hydrogen for other use, industrial use, so it can be shipped, it can be distributed. So that's more or less what you can have in terms of solution for decarbonization. So switching from from a fossil source to a non-fossil source. And when I discussed the electricity at the beginning, of course, it will depend on how the electricity is produced, because today, as you know, most of the electricity is still produced with fossil fuel.
Yes, so it looks like there is no silver bullet. There is no easy solution, and all these solutions come with a higher OPEX, potentially higher CAPEX, and sometimes issues of availability and questions of availability. And even indeed, renewable electricity is not a given, and it's not a given that sites might have access to the quantities they need, and they might have the infrastructure which is needed to distribute this high quantity of extra electricity within the site. So let's speak now about the last part of the methodology, which is probably the first one to implement. This is what we call optimize, and this is really about optimizing thermal efficiency. And you and me were very passionate about that part because we believe it's a little bit unknown today and not covered enough. Why we believe that can be a significant source of thermal decarbonization. So can you tell us about waste heat, the different type of waste heat, and how this waste heat can be identified, quantified, and how to design a system to recover it?
Yes, indeed. You're perfectly right. This is a big untapped potential that we have today. Is the optimization of this of the way we are using the heat in the industry. So basically, to run a process, you need cooling and you need heating, and the beauty of that is that you can match them together in order that you can benefit from one. So take the heat from one process It will cool this process. If you remove the heat, it will cool the process and put that heat in another process where it requires heat. So that's really the point here. And how do we want to address that systematically is by applying what we call the pinch methodology. So the pinch methodology will allow us really to match all the heat source with the heat sink. So basically the need of heating with the availability of heating within a site at the level of temperature that is required. And by doing that, we will optimize the possibility to exchange the heat within the factory that we are looking within the process, if you want, that we are studying. And by doing that, you will really minimize the total energy requirements of your system. Then when you have done that, this direct heat exchange that is possible, you still have usually a lot of low-grade heat. So the heat that is available at low temperature, 40 degrees or something like that, which is typical when you have a cooling system. A cooling system, as I mentioned before, you take the heat from a process and you will put it somewhere else. So, and the somewhere else is typically a huge quantity of heat that you have at the level of 30, 40 degrees. And now the idea of the pinch is also to take that heat, low-grade heat, and to use a thermodynamic system called a heat pump, where you will take this heat, that's why we call that a heat pump. We pump that heat at this level of temperature, and we put it at a higher level of temperature. And by doing so, then we have now heat available at high grade, or high grade for what we are talking here, which is 150 degrees, the temperature that we are that we were discussing before. That is very useful in those type of industry. So by now mixing that together, so the direct heat exchanger plus the heat pump, we can reduce the heat consumption of a global site by a factor of 2. Almost 50% of the energy that is consumed in that plant can be saved by applying this methodology.
Yeah, and what appears very interesting is these are existing methodology and existing technology. Pinch, I think, has been almost invented, or at least heavily used in the petrochemical refining chemical industry with continuous process, and now it's being adapted to this kind of batch processing lighter industry. And heat pumps is the refrigeration cycle, which is all around us in equipment such as air conditioning and fridges that we have at home. So it's very, very common, but now it's being applied again to this light industrial challenge with high capacity and high temperatures. You mentioned cooling, and I find this is really kind of underestimated. You know, I'm not an engineer, so at the beginning I was thinking that cooling is just this machine making some kind of magical, having a magical way to produce cold air or cold water. And then one day somebody explained me that this is really about extracting heat out and bringing this heat out of the building and sending it to cooling towers, which, by the way, are a significant consumer of water for these industrial sites. So a part of the water consumption can be decreased if cooling towers are eliminated, and this low-grade heat is now made valuable. You mentioned steam at the beginning, and we find out that this is one of the hurdles for applying waste heat recovery, is the fact that currently heat is generated and distributed at relatively high temperature. So 180 degrees C, that's 10 bar gauge saturated steam. 180 degrees C, it's about 350 Fahrenheit. And today, most of the sites are looking how to generate that steam in a decarbonized way. The key we found out is not to try to replicate what is being done now. It is rather to group the heating and heat sources by category, maybe in 2-3 different categories, and to distribute the low and medium grade heat through hot water circuits. And these low and medium grade heat, by the way, are like 80% of the demand of industrial sites or light industrial sites. only 20% really need more than 120 degrees C or 250 degrees Fahrenheit. So by splitting the demand, and that's what Pinch tells us to do, is to go and look at the real set point of the process. By splitting these heat sinks or these processes by different categories of temperature and matching them with the heat sources by different category of temperature, we can build 2 or 3 networks, 2 out of 3 in hot water and maybe the last one in steam. And by becoming more granular, we are removing a major obstacle at the beginning, and from there the domino kind of starts to fall, and we can apply direct heat recovery and even low-grade heat recovery using heat pumps. So these 3 steps, replacing steam by hot water below 120 degrees C or 250 Fahrenheit, recovering, making direct heat recovery and low-grade heat recovery, that's what we at Armstrong we call circular thermal. And I think it's a very simple term that allows many people to understand what it is that we are trying to achieve. Take the stream of waste heat and bring them back, channel them back to the process where this energy is needed. So this sounds like a great idea. And however, very few plants have been designed so far this way. Maybe some of the newest plants have been designed in order to apply circular thermal. So Alain, can you tell us what were the hurdles so far? Why circular thermal and waste heat recovery was not so applied in this light industry, why it is widely available? And how optimistic are you for the future? How do you believe that this design method is going to be applied in the future, including for refurbishing existing sites?
Yes, indeed. I mean, in reality, this methodology, if you want, the pinch, has been invented 40 years ago, and was really applied, as you mentioned, more in the chemical industry. So, what's the reason for that? Is mainly because in the FMCG business, or in the food and on consumer good manufacturing, the energy represents a small part of the total cost of production, less than 5%, for example. So it's not really the major focus on when you want to improve your cost of production. That's not when you do a Pareto. That's not the first one that will come. Which is not the case when you are working in the heavy chemical industry. They have to be efficient because they will eat their margin if they are not, which was not the case in the past for the FMCG business. But now with the increased cost of energy, the tax that you can see on the carbon that is starting to come, there is more and more interest in improving those process, and also the fact that in the past, for those companies to be compliant was to deliver the savings that they committed, and we were talking about an incremental savings, let's say 3% per year. They have to deliver, and they can achieve that with different process without going through a major and holistic approach like the pinch, for example. So that's basically what they were doing. But now the game has changed. Most of those 500 companies, they've committed for 0 target. They have to go for 0. So it's no more question if this is worth to do it or not from money wise. It is making sense money wise, but that's not the main driver. The main driver is that they have to deliver what they've committed, and I think that's the big game changer now. And pinch, I think, on the approach on the global holistic approach on minimizing and optimizing this heat demand within the operation is a must if you want to reach the 0 target. It's not affordable if you are not passing through this step. I think that's it.
So it looks like the optimized approach in waste heat recovery, circular thermal, would allow to decarbonize thermal in light industries with a positive payback. which is probably not the case when you switch to renewable heat. The operating cost is increasing, so the payback is kind of negative. I think there is also a bigger reason behind that, which makes us quite excited, and it is a very inspirational goal, is to think about the fact that light industries are sitting in a kind of sweet spot. They have both waste heat, which is not the case in other sectors of society, like transportation or buildings. There is not a huge amount of waste heat there to be recovered. In light industry, there is a significant amount of waste heat, and they do need heat at a relatively low temperature, which is not the case with heavy industry, which need heat at very high temperature. So the availability of waste heat and the need for heat at relatively low temperature, below 150 degrees C, makes the light industry sitting in this sweet spot where they can avoid consuming renewable energy by recovering their waste heat and reusing it through circular thermal. And that can have a huge impact. You and me, while preparing today conversation, we did a kind of back of the envelope quick calculation, and it appears that the potential for waste heat recovery in light industry is more than a year of additional renewable capacity that the world is adding. So this year in 2021, all new renewable energy, wind, solar, hydro, biomass, that will be less than the quantity of waste heat which is available and can be recovered in light industry. So that's a kind of bigger goal, and I know it's very inspiring for us, for many people at Armstrong, but also for many people working on our customer organization, sustainability department, for our partners who are working with us towards this challenge. So in order to conclude, Alain, a last question for you. Let's imagine for a moment you sit back in one of these chairs of having a role, being a global sustainability or global energy manager for one of these Fortune 500 companies with hundreds of sites around the globe. How would you tackle thermal decarbonization? How would you build that roadmap? How would you implement it? What are the kind of best practices that you have from your previous experience?
So first, I would be very pleased that they have all committed to the zero, and this will help me in my job. And I think one key success factor is collaboration here. I'm sure that you are remembering the time where we were working together at that time, you at Armstrong, me at Nestle. And when we started to implement this program that we were calling energy target setting, which was really an holistic approach in the factories with different experts. You guys were the thermal expert, but we had water expert, we had the electrical expert, and so on. And on the fact that we were all together working on the same topic within the same room, with the people from the process that were involved, because usually it's quite difficult to have the people, the owner of the process, discussing with the utility side. But here we were all together, and I think this was the major improvement that we observed. So really now working together, working hand in hand with your supplier. I think this would be the first thing that I would look for. Then you also need motivation. You need people that are in front of you that are really enthusiastic about that. We need people that are motivated and they will put their guts on the project to make sure the things are moving. You need, the human factor is enormous in this work, and it's very, very important that you have the people engaged from the beginning. And then in terms of rollout of the system, of course, doing some pilot will be very, very important. But as soon as you have done some pilot, I would group them by process type, in order that we can replicate. If you are working in a company producing culinary, you will go for culinary, and you know that they have usually a process that are very similar. So something that has been done in one place can be replicated quite easily in other one. You need to adapt, of course, but it would make sense really to go by business unit in order that you can streamline the way you are delivering the solution. And finally, for all the new build, the new factories, making sure that we are designing from the beginning, considering the fact that we can have this wasted utilization rather than to build it with the old design and then to come to refurbish the system. So good design would be really really something that we need to push for. And of course, I'm already listening the people in charge of the capex telling me, "Ooh, but it will cost a hell of money to do that." Yes, it's true. That's a significant investment, but I'm sure that we will now see more and more solution as a service with an external company investing for the asset, and you will basically buy the heat on the service of getting heat, like you get it today with the electricity, with the power purchase agreement. In the future, I really see that as a service solution, in order that we can reduce also the capex and focus on our core business.
Yeah, thermal PPAs, that's the dream of many people to decarbonize that industry. Thank you very much, Alain, for having this conversation today. Thank you to all our viewers. We just scratched the surface today. We mentioned a lot of subjects which are going to be covered in future episodes of the Armstrong live stream. So stay tuned and make sure that you're following the new episodes. And in the meantime, please visit the decarbonization section of the Armstrong website, armstronginternational.com. Thank you, Alain.
Thank you, Rossen, for the opportunity, and thank you all for listening to you. Very excited to be part of this journey with you. Bye-bye.
Bye-bye.